let's talk about an application of some of these resonance tubes, because that's where the musical instruments come into play. And these are mainly the wind instruments. The woodwinds, the brass. These are the types of instruments where this open-closed and open-open type of geometry applies. Also with the pipe organ. Now again, think about the purest sound wave is a harmonic wave. It's single frequency, it has only one period. That is really what we can break all sound down into, okay? What we want to analyze is the sound that's coming from some of these musical instruments and be able to compare and contrast. Now, somebody by the name of Joseph Fourier developed a mathematical technique that has great applications in music and sound, but was actually designed to study heat flow. And Fourier's technique is still used today for analyzing so many different things. We use a version of his basic principles to do what's called a fast Fourier transform. In any case, you can take any type of temporal information, any sound, and break it into its individual frequencies. Here is a graph of the amplitude versus time of somebody's voice. A computer can put that through what's called a fast Fourier transform and break it into all its frequency components, okay? That's how speech recognition actually works, by analyzing how the spectrum of your voice evolves with time. You actually have a fingerprint which is unique to you and would be very difficult for somebody else to mimic. Okay. And you can do really fancy fast Fourier transforms with waves and come up with three-dimensional plots showing how the frequencies evolve with time. But for our purposes, we're going to understand that by looking at sound, looking at the frequencies, we can see how a musical note is different from most other sound waves. Okay, if we have a pure harmonic wave, and this would be a sine function or a cosine function, okay? Oops. Remember, we're kind of looking at a wave that's going to be A cosine kx minus omega t, that sort of form, okay? Where the wave's going to be propagating in some direction. If you do a Fourier transform on this, you see that this nice periodic wave produces a sharp peak, okay? It's only one period, right? It only has one period, t, and f is equal to 1 over t. Well, if it only has one period, we would expect when graphing the intensity of this wave as a function of frequency, remember, the fast Fourier transform allows us to turn time into a frequency, we would see a single peak. So according to Fourier transforms, the purest type of wave would be a sine or a cosine wave. We get one single peak, and the width of this peak, what we call the bandwidth, actually depends on how long that wave plays. I mean, if it were an infinite wave in time, that peak's thickness would go to 0. Not important for our discussion, but just think of this. This is a wave, let's say 1, 2, 3, 4, 5, 6. This is a wave, let's say, that oscillates at, I don't know. Well, let's call this a AC voltage, okay? So 0.0167 seconds. That's the period from one peak to the next peak. If we do a Fourier transform, we find out that that would have a frequency around 60 hertz. Okay? All right. So if we strike a tuning forks are great for tuning instruments because they have nearly a single frequency. Honestly, they have some overtones or some harmonics, some weak harmonics at higher frequencies. But for the most part, it produces a nice, strong single frequency. Okay, big, impressive, fundamental, not a whole lot of harmonics. Okay. However, if we look at noise and we do a Fourier transform of noise, what we see is that instead of a single frequency, we have all frequencies. Okay? You ever hear static or noise? That's what it is. It's all frequencies played at once. It doesn't sound great to our ears all the time, although some people use what we call this white noise, which means all frequencies of sound, to actually calm us, because for some reason, some people, when they listen to white noise, it has a calming effect. Some noise is actually called pink noise because it has more intensity at low frequencies and less intensity at high frequencies. But in both cases, there's no single peak here. Okay? Now, where we can identify a definite frequency, okay, we would call this definite pitch. All right. Looking at the noise, no peaks. Okay. No definite frequency. No definite pitch. Okay. Or an indefinite pitch, if you will. You might have heard those terms used for music from time to time. For a musical note of definite pitch, we have, well, basically a mathematical pattern that we can identify. At one frequency, what we call the fundamental, we have this strong peak. So that would be F1. At twice that frequency, we also have a peak. At 3 times that frequency, the peak's a little bit lower, but it's present. At 4 times that, we see another one. This is what a musical note of definite pitch looks like when we take a frequency spectrum of it. Okay? And that's why standing waves are a great way to generate a musical note. If we're talking about a standing wave on a string, such as we find on a violin or a guitar, those standing waves, like here's the n equals 3 standing wave, naturally occur without anything crazy to create them. Okay? So string instruments have this natural progression. N equals 1, n equals 2, n equals 3. And depending on what musical instrument it is, some of these harmonics can be boosted, while some of these harmonics can be less, giving each sound for a musical instrument, what we call the timbre, a different identity for different musical instruments. So when we listen to a musical note, we're actually hearing a few harmonics, a few sines and cosine waves put together where the frequency is related by an integer value. All right. Now, the fact of the matter is you can actually take any shape wave and break it into its individual harmonics. Okay. Here is a square wave. And again, using Fourier's techniques, you could actually break it into individual sine waves, add them all together, and you'll get that square. Okay? So what this means is, not only do musical instruments have very distinct harmonics, but we can use sines and cosines to mimic or synthesize. You get the picture here? Musical synthesizer. Synthesize almost any sound that you want. Okay. Let's take a look at a musical note. This is musical note middle A. Okay? It's known as A4, also known as A above C. Its fundamental is 440 hertz. That is its F1, 440 hertz. Not surprising, the second harmonic is twice that. 440 times 2 is 880 hertz. Times 3 1320 hertz times 4, 60 hertz. Okay, so any musical instrument playing this A4, okay, is going to have these different harmonics. But why would a clarinet sound different from a guitar, which would sound different from a trumpet playing the same note? Well, the intensity of each of these harmonics will be different for these different instruments. Instruments that tend to have a warm, deep tone to them generally are stronger in the fundamental and weaker in the higher harmonics. Instruments that have a very bright timbre not only have a fundamental, but very strong second, third, fourth, all the way out to very high harmonics. So here might be the frequency spectrum of A played on one instrument. The first harmonic, or fundamental, is the strongest. The second harmonic is significantly weaker. Third harmonic, a little bit stronger than that, and then fourth harmonic, and so on. Okay? Every instrument sounds different because these different relative levels are higher or lower depending on what instrument we're talking about. Here is, for instance, a flute. In this particular case, the flute is playing a note which has a very bright timbre sound to it. And it's so bright, actually the second harmonic exceeds the first harmonic in intensity. Okay? So again, with the flute, a very bright sounding instrument, we would expect tons and tons of higher harmonics. Here is another frequency spectrum for a flute. And again, you can see that the first three harmonics, this one, and this one, it's playing G4, are still pretty intense. In fact, you can go out to the 4, 5, 6, 7, 8, 9. We can still see the 10th harmonic, the 11th harmonic, way out there. Again, lots of high harmonics means that this particular instrument sounds very bright. Now we look at the violin, also a bright sounding instrument. And again, first harmonic, second harmonic, third harmonic, fourth harmonic, all of them still very intense, even all the way out to 5, 6, 7, 8, 9, 10, 11, 12th harmonic. Bright sounding instrument. However, when we look at some of the other instruments, such as the clarinet, we notice that some of the harmonics are actually missing. Okay, here's the first harmonic, the second harmonic's missing, the third harmonic, fourth harmonic's missing, fifth harmonic, and so on. This happens because this end of the instrument is closed, this end of the instrument is open. Again, these odd harmonics where we only allow n equals 1, 3, 5, all the odd numbers, clearly gives a clarinet a very different sound than the flute. Here's a didgeridoo. Now, a didgeridoo is an Australian instrument. It's made from a stick that's been hollowed out by termites. So they cut the tree down, they clean it up. And what's interesting is it kind of borders on being of definite pitch and indefinite pitch. Now, here we show something of definite pitch superimposed on the didgeridoo. Okay, 1, 3, 4, 5, 6. Sometimes there's a peak at these harmonics. The first harmonic, the third harmonic, definitely the fifth harmonic, and so on. Similar to what we have with the clarinet. But we also have these non-integer harmonics, which gives a didgeridoo a very different sound to it. It's not clearly pure definite pitch, but it's certainly not indefinite pitch either. Okay? Sort of obeys its own mathematical principles. So again, In music, the characteristic of sounds that we refer to, the quality of sound or the timbre, really is looking at what are the different mixtures of harmonics. Just as everybody has their own unique voice, every instrument has its own unique sound based on what each of the harmonics are doing. Pitch is mainly related, but not always, to the fundamental frequency, okay? You know, when we think about the fundamentals, you got to be a little bit careful because some would argue some of the instruments are missing their fundamentals. Sometimes your second harmonic's stronger. But again, usually when we hear a particular pitch, we're asking what is that fundamental frequency.